Hello, this is IT Taro. I would like to investigate the humidity sensor this time. Since it is a continuation of the previous temperature sensor, I would like to check only the points for the same content. Also, I will supplement and understand the I2C part that I could not fully understand last time. Let's move on to the table of contents. Here is the table of contents. In the first item, we will check the sensor to be investigated. In terms of specifications, we also understand what kind of product it is. The second item is to understand the port and I2C used by ESP32. Next, we will understand the use of each sensor, check the measurement circuit, etc., and present the measurement results. At the DHT20 sensor, we will specifically check the I2C signal specifications and understand the program. As reference information, I would like to introduce countermeasures for cases where there are many cases where writing to ESP32 fails. Finally, I would like to summarize the temperature and humidity sensors as a whole and consider which one is the best for electronic work. Move on. Here is a list of sensors that we will investigate this time. However, since this is the same as the temperature sensor, the humidity sensor is the bottom 4. We choose from nearby stores and reliable mail order sites. We have excluded overseas mail order sites because there is a possibility that sensors that are not genuine products may be delivered. 3.3 volts or 5 volts can be used, and as a result of selecting the cheapest one, I ended up on the same list as the temperature sensor. This is because humidity can be measured in combination with temperature in many cases, and the price is low. If you use it, I think you will use both temperature and humidity, and I don't think you will use even if you choose more sensors, so I will investigate the following 4 sensors. Move on. I'll check some specs. The humidity sensor acquires and measures the humidity data inside the sensor. There are 2 types of data acquisition, I2C and serial communication. Programming is easy because you can use and obtain what is provided in the library. For sensors without a library, we will program and acquire I2C. The program itself tends to be complicated, but I think it's good for troubleshooting and improvement because it deepens the understanding of the operation itself. Move on. When using ESP32 I2C, it is necessary to use the assigned port fixedly, but serial communication can use many PO terminals, so the degree of freedom is high. Here is the port configuration. I2C needs to use 21 and 22, but serial communication can be selected from normal PO, so you can freely choose from many pins. Move on. Let's understand a little bit about I2C. The configuration is a master-slave configuration, and the ESP32 is the master. All connected humidity sensor devices are connected as slaves. With bus wiring, all devices are connected by branching from the SDA and SCL trunk lines. The address of the connected device must be unique, and communication will not be possible if it is duplicated. Communication is started by sending a trigger from the master to the slave with the specified address, and all slave devices receive it, but only when the addresses match, the communication is carried out in the form of a response. Because of this format, communication cannot be started from the slave. Communication is always performed in response to an inquiry from the master. I will understand this content and start programming. Move on. Regarding AHT25, it is a type that acquires data via I2C. The address is fixed at 38 hexadecimal numbers. The inquiry from the master, that is, the trigger signal to start communication, and the reply temperature and humidity data are as follows. A CRC is added at the end of the reply signal. This is a code for detecting whether there is an error in the data. We will use the library to program the CRC calculation, so add the library described below and program. Move on. For reference, check how to install the library. As shown here, start the library manager, search for CRC, and install the corresponding library. Move on. Regarding OT21B, it also acquires data by I2C. However, since the library is provided, we will use it. Install and program this library. Move on. It becomes DHT20. It also acquires data via I2C. The address is 38 in hexadecimal. I will check the data acquisition programming of I2C with this sensor. Move on. Here is the data acquisition program. I referred to the reference URL on the upper right. As I understood with I2C, data is obtained in the form of an inquiry from the master ESP32 and a response from the slave humidity sensor. Therefore, the inquiry signal is sent from line 67 to line 71. Here, the signal described in the datasheet is sent to the DHT20 address as a trigger. You will receive a signal when the transmission is complete. Signal reception is obtained from line 74 to line 75. Received signals are buffered in an array. Since the first byte of the received signal contains the status, line 77 determines whether the reception is complete. If it completes normally, exit the while statement, get the data from line 80, and calculate the humidity data. Humidity data is stored in multiple arrays, so take them out one by one and shift the bits to make them normal data. The processing is performed from line 80 to line 84. Put the data in 32-bit long type and get the numerical value. The obtained value is divided by 2 to the 20th power according to the specifications on line 85, and then multiplied by 100 to calculate the humidity. Lines 87 to 92 similarly acquire and calculate temperature data. The number calculated in the last 94th line is displayed on the serial monitor. That's it for the program. Move on. DHT11 becomes a sensor that acquires data by serial communication. Serial communication can be easily used with the provided library. I installed and programmed the library at the bottom. Move on. Failures often occur when writing to an ESP32 development board, so let's review the most likely problems. When you press the right button in Arduino IDE, compilation starts first. This is the work of converting software into a form that is easy for machines to understand and execute. Once compiled, an executable file will be created. In other words, it will create a file to write to the ESP32. Next, connect to ESP32. Connecting is displayed in the message column. If it can connect, it will move on to the next writing, but there are times when dots are displayed many times and it does not proceed from connecting. In this case, keep the boot button pressed while the connecting dots are displayed many times. If the ESP32 is successfully connected, it may proceed to write. There are many cases where writing fails due to this problem, so I will introduce it. For your reference, I also share other errors in the table below. Move on. It will be a circuit diagram. This circuit diagram is exactly the same as the temperature measurement. This circuit measures A21B. Wire the power and ground, and wire SDA and SCL to terminals 21 and 22 of the ESP32 for I2C communication. If other sensors also use I2C, the circuit will be similar. Move on. This circuit measures AHT25. Since it will be the same as the previous circuit, the confirmation is omitted. Move on. This circuit measures DHT20 and DHT11. Since DHT20 acquires data with I2C, it is the same as before. Since the DHT11 acquires data through serial communication, any normal terminal is fine. I am using 32 this time. Move on. In order to measure as accurately as possible, we prepared 4 commercially available hygrometers. However, this is also not high performance, so I do not know how accurate it is. For this reason, the measured values that clearly deviate are excluded, and the remaining average value is used as the humidity of the measuring instrument. We will measure how much error there is from this humidity. Humidity is increased by a humidifier, but it is difficult to maintain a constant humidity for a long period of time, so measurements are taken while the humidity is changing. Therefore, there are product differences in the speed at which changes are followed, and if these factors are taken into consideration, a certain amount of measurement error will occur. The measurement environment is the same as when measuring the temperature, and the sensor is placed in a shape that surrounds it with 4. Move on. Here are the measurement results. I have some doubts about the accuracy of the meter itself, as the hygrometer in the meter is out of step with the other 4 sensors. But overall, I think it's a good trend. Aside from the fine accuracy, we believe that all sensors are able to measure at a level that is not problematic in normal use. As a result, the order of error was DHT20, AHT25, and DHT11. I made a graph of the error including the thermometer, so let's move on to the next step. It is confirmed as a temperature and humidity sensor total. The percent error was calculated and summed for all measurements. The percentage of error is 10% if there is an error of 2 degrees Celsius at a temperature of 20 degrees Celsius, for example. These ratios are totaled and graphed. AHT25, DHT11, and DHT20 are the order with the fewest total errors. Move on. Finally, I considered which sensor is the best for electronic work and what I would like to use. AHT25 requires a dedicated cable on a breadboard and is difficult to work with. Also, as a result of considering the price and ease of programming, I personally wanted to use DHT20 the most. However, considering that I2C programming is a little complicated, I think DHT11 would be fine. I think it will change depending on what you focus on, but I introduced it for reference. This concludes the investigation of temperature and humidity sensors. In the future, I would like to do work using these.
We will continue to take on the challenge of making things using IT like this, so please give us a high rating and subscribe to the channel. See you next time.